the hypothetical scenario of being instantaneously thrust into a state of absolute zero, the theoretical lowest possible temperature designated as 0 Kelvin, or minus 273.15 degrees Celsius, presents a profound intellectual exercise at the very nexus of thermodynamics, quantum mechanics, and the very perception of existence, demanding an exploration that transcends mere freezing to confront the fundamental laws governing molecular motion and the nature of time itself. If one were to, against the established principles of the universe, experience this ultimate cessation of thermal energy, the immediate, and indeed the eternal, consequence would not be the painful, slow descent into cellular necrosis associated with cryogenic freezing, but rather an instantaneous, absolute suspension of all kinetic activity within the biological substrate, an event so final that the very concept of experience dissolves. To properly frame this hypothetical immersion, we must first rigorously define temperature not as a vague measure of coldness, but as a precise macroscopic manifestation of the average kinetic energy possessed by the constituent particles, atoms and molecules, of a system. In a human body operating at standard physiological temperature, approximately 310 Kelvin, the molecules constituting every cell, every protein, every strand of DNA, are engaged in a furious, ceaseless ballet of motion, vibrating, rotating, and translating across minute distances at speeds dictated by the thermal reservoir. Consider the chaotic energy transfer during a typical heartbeat, the influx of calcium ions initiating muscle contraction, the rapid conformational changes of enzymes facilitating metabolic pathways, the propagation of electrochemical signals across neuronal synapses. Each is contingent upon the precise timing and energy of molecular interactions governed by thermal agitation. At 298 Kelvin, the thermal energy is sufficient to ensure these myriad biochemical reactions proceed at the requisite rates to sustain life, rates measured in milliseconds, where billions upon billions of atomic collisions occur every second, the very definition of biological dynamism. However, absolute zero, 0 Kelvin, represents the theoretical asymptote where the mean kinetic energy of the particles within a system reaches its minimum possible value. This minimum is not zero, a crucial nuance to be addressed later, but in the context of macroscopic experience, it signifies the complete absence of translational, rotational, and vibrational motion stemming from thermal excitation. Imagine a single water molecule suspended in the hypothetical absolute zero environment. At room temperature, this molecule zips around with significant kinetic energy. As it cools, its speed diminishes, its molecular bonds stiffen, eventually locking into the crystalline lattice we recognize as ice at 273.15 Kelvin. Lowering the temperature further reduces the residual vibrational energy within that lattice structure. Now, extrapolate this arrest of motion across the trillions upon trillions of molecules composing the human form. The rapid oscillation of the lipid bilayers in cell membranes would cease, the complex folding and unfolding dynamics essential for enzymatic function would halt, the propagation of action potentials along axons, which relies on the precise opening and closing of voltage-gated ion channels driven by kinetic energy, would become impossible. The individual, or rather, the constituent matter that was, the individual, would instantaneously transition from a dynamic, complex, self-regulating thermodynamic system into a static, perfectly ordered, albeit still chemically bonded, structure. The event would not be experienced as a chilling, but as an immediate cessation of all sensory input, for sensation itself is an electrochemical process dependent on molecular movement. The photons striking the retina, the mechanical deformation of Pacinian corpuscles detecting pressure, the binding of odorants to olfactory receptors, all processes requiring energy input and subsequent molecular reconfiguration, would instantly become nullified events. The brain, the seat of consciousness, would not register the transition, the neural cascade that constitutes awareness, the continuous electrochemical firing patterns that define the present moment, would simply stop, not gradually fade, but cease as if a master circuit breaker governing all fundamental particle movement had been thrown. In this state, the body would become, quite literally, perfectly preserved, yet utterly inert, statue composed of matter whose constituent atoms are locked into their lowest possible energy configuration relative to the ambient field, a singularity of stillness. This leads directly to the contemplation of time. Our very apprehension of temporal passage is inextricably linked to entropy and observable change, the second law of thermodynamics dictating the relentless increase of disorder in isolated systems. We measure time by the aging of stars, the decay of isotopes, the beating of a heart, the chemical reactions occurring within our own bodies. If all molecular motion ceases, if all chemical reactions, the basis of biology and observable physics, are suspended, then the fundamental metric by which we quantify duration loses its reference point. If no process unfolds, no state transitions occur, then for the matter existing at absolute zero, time, as an experimental or even physical measurable quantity, ceases to possess operational meaning. It is a perfect, eternal stasis, a frozen slice of reality impermeable to the arrow of time that characterizes the macroscopic, high-energy universe. Yet, this seemingly simple conclusion, that all motion stops at absolute zero, is precisely where the comforting determinism of classical physics dissolves into the probabilistic strangeness of quantum mechanics, revealing that invisible wall that the universe erects against true zero. The German physicist Walther Nernst, in proposing the third law of thermodynamics around 1906, mathematically formalized this barrier, stating, in its most accessible interpretation, that reaching absolute zero is asymptotically impossible for any system. This is not an engineering difficulty related to the inefficiency of cooling apparatus, it is a statement about the fundamental nature of energy exchange in the universe. As a system approaches 0 Kelvin, the rate at which one can remove the remaining infinitesimal amounts of thermal energy decreases dramatically, requiring an infinite amount of work or an infinite amount of time to extract that final quantum of thermal vibration. The deeper reason for this inviolability lies in the quantum realm, specifically manifesting as the zero-point energy. Quantum mechanics dictates that particles, even those bound within atoms or lattices, cannot possess perfectly defined zero momentum and zero position simultaneously, a constraint articulated by Werner Heisenberg's uncertainty principle. If a particle were truly at rest, its momentum would be exactly zero, and its position would be perfectly known, a violation of this foundational principle. Therefore, even in a state where all external, or thermal, energy has been removed, particles retain a residual, irreducible minimum kinetic energy known as zero-point energy, or ZPE. This ZPE manifests as a persistent, unavoidable quantum jitter. For a system cooled to the theoretical limit, the atoms would still be oscillating, albeit with amplitudes many orders of magnitude smaller than those experienced at 1 Kelvin, far below the measurable thermal noise of the environment. This quantum mechanical imperative means that the hypothetical scenario of dot instantaneously stopping all atomic motion, as implied by the thought experiment, requires violating not only the third law of thermodynamics but also the uncertainty principle itself. If one were truly subjected to absolute zero, the matter composing the body would settle into its lowest vibrational state allowed by quantum mechanics, maintaining a persistent, non-zero kinetic energy inherent to its existence within space-time. The resulting structure would be incredibly cold, profoundly sluggish, but not perfectly static in the classical sense. The relentless pursuit of this unreachable limit by physicists has yielded some of the most extraordinary discoveries in modern science, providing glimpses into how matter behaves when thermal noise is suppressed to near negligible levels. Consider the staggering technological feats achieved in laboratories globally. The current world record for the lowest temperature achieved, set by a team in Germany, hovers around 0.000000000038 Kelvin, or quantitatively, 38 femtokelvin. This measurement, which equates to -273.14999999999962 degrees Celsius, illustrates the extraordinary refinement required to tease out the last vestiges of thermal energy from a physical system, often involving complex laser cooling techniques applied to ultra-cold atomic gases like rubidium or strontium. One of the earliest and most dramatic manifestations of quantum behavior near absolute zero is superfluidity, first observed by Piotr Kapitsa in 1937 when studying liquid helium. As liquid helium-4 is cooled below approximately 2.17 Kelvin, the lambda point, it undergoes a phase transition into a superfluid state. In this state, the fluid exhibits zero viscosity, it flows without any energy dissipation. This is not merely extremely low friction, it is the complete absence of internal friction. The experimental observations were baffling. The superfluid would creep up the inner walls of its container, flow uphill against gravity, and escape through capillary tubes so narrow that even the largest impurity atoms could not pass, behaving less like a liquid and more like a quantum wave function on a macroscopic scale. If a container of superfluid were set into slow rotation, the fluid itself, due to its zero dissipation, would continue rotating indefinitely, a perfect demonstration of kinetic energy conservation unmarred by thermal damping. Closely related, yet distinct in its macroscopic consequence, is superconductivity, first reported by Heike Kamerlingh-Onnes in 1911 when cooling mercury to 4 Kelvin. Below a critical temperature, the electrical resistance of certain materials vanishes entirely. This means that an electrical current introduced into a closed superconducting loop will persist, theoretically, for geological timescales, the current decaying only through interactions with external electromagnetic fields or structural instabilities, not through the resistance inherent in the material. The mechanism, largely explained later by the Bardeen-Cooper-Schrieffer or BCS theory, involves electrons overcoming their natural mutual repulsion to form Cooper pairs, which then condense into a single quantum state capable of flowing coherently through the lattice without scattering off imperfections or phonons, the quanta of vibrational energy. This zero resistance is foundational to modern high-field technologies, powering everything from magnetic resonance imaging machines to the development of high-efficiency power transmission lines and, critically, the massive electromagnets required for harnessing nuclear fusion energy, where maintaining massive magnetic fields requires minimal energy input to sustain the current. Perhaps the most bizarre and conceptually challenging consequence of pushing matter toward absolute zero is the formation of the Bose-Einstein condensate, or BEC, a state of matter predicted in the 1920s by Satyendra Nath Bose and Albert Einstein, and finally achieved experimentally in 1995 by Eric Cornell, Carl Wieman, and Wolfgang Kettel, earning them the Nobel Prize in 2001. When certain types of atoms, specifically bosons, are cooled to temperatures in the nanokelvin range, their de Broglie wavelengths, the quantum mechanical description of their spatial extent, become so large that they begin to significantly overlap. At this juncture, the individual quantum identities of the atoms dissolve. Thousands or even millions of atoms coalesce into a single, unified quantum entity, superatom, occupying the same minimum energy state. All the constituent particles move in perfect synchronicity, described by a single, collective wave function. The BEC state is the ultimate realization of quantum coherence on a scale visible to macroscopic observation. The manipulation of these condensates has led to astonishing demonstrations of physics in action. For instance, the speed of light, a universal constant of approximately 300,000 km per second in a vacuum, can be drastically altered within a BEC. In a celebrated experiment performed by Harvard physicists, the speed of light propagating through a rubidium BEC was successfully slowed to a mere 61 km per hour. The light is not merely passing through a dense medium, the photons are temporarily absorbed and re-emitted by the atoms in the condensate, their propagation synchronized with the collective quantum state of the superatom, effectively surfing the collective wave function until they exit the medium. The ability to manipulate light and matter at this fundamental level underscores the profound physical reality that exists just shy of the absolute zero barrier. Returning to the human body thrust into this impossible thermal vacuum, the consequences extend beyond cessation of biological function to radical alteration of physical states. Solids, which depend on a certain degree of thermal vibration to maintain flexibility and elasticity, the slight yielding of a metal beam under stress, the subtle give of biological tissue, would become utterly brittle. The interatomic forces would hold the structure rigid in its lowest energy configuration. Any attempt to exert force beyond the binding energy would result not in bending or deforming, but in catastrophic brittle fracture, the material shattering along its crystalline planes with minimal external energy input, as the structure lacks the mechanism, thermal vibration, to dissipate mechanical stress. Liquids, which rely on kinetic energy to overcome intermolecular attractive forces and maintain fluidity, would instantly solidify into perfectly ordered, possibly amorphous, solids if the material did not already possess a defined crystalline structure at that energy level, effectively creating a universal, instant phase transition to extreme rigidity across all fluids, including blood, cytoplasm, and atmospheric gases surrounding the body. The environment itself, were it to conform to absolute zero, would transform the familiar world into a silent, crystalline tableau. The air, composed primarily of nitrogen and oxygen molecules moving at hundreds of meters per second at room temperature, would collapse. The gas laws, derived from the kinetic theory of gases, would dictate that the pressure drops precipitously towards zero as the kinetic energy vanishes. At 0 Kelvin, the atmosphere would likely transition into a solid state, layers of frozen nitrogen and oxygen forming a brittle, silent ground layer. The entire universe, viewed from the perspective of this 0-Kelvin entity, would be frozen in its current spatial arrangement, perfect, unchanging photograph rendered in ultra-low energy matter. If we consider the implications for future technologies predicated on operating near absolute zero, the potential is transformative, far exceeding current laboratory constraints. Quantum computing, for instance, relies fundamentally on maintaining the fragile quantum states of qubits, superpositions of 0 and 1, against environmental decoherence. Heat is the primary antagonist to coherence, as random thermal motion introduces phase noise that collapses the superposition. Therefore, cutting-edge superconducting quantum processors, such as those utilizing transmons or flux qubits, require deep cryogenic cooling, often achieved using dilution refrigerators operating at temperatures around 15 millikelvin. Achieving temperatures closer to the absolute zero limit would drastically increase coherence times, allowing for far more complex algorithms to execute before the quantum information degrades, potentially unlocking computational power capable of simulating molecular interactions at an unprecedented scale, revolutionizing drug discovery and materials science. Furthermore, in the realm of clean energy, the dream of sustained nuclear fusion power, harnessing the energy source of the stars, is heavily dependent on superconductors. Tokamaks and stellarators, the magnetic confinement devices designed to contain superheated plasma at temperatures exceeding 150 million degrees Celsius, utilize immensely powerful magnetic fields to prevent the plasma from touching the reactor walls. These fields are generated by superconducting magnets. If the materials used for these coils cannot maintain superconductivity, the power required to run the magnets would vastly exceed the energy output of the fusion reaction. Pushing the operational temperature of these superconducting materials closer to the quantum ground state offers the potential for more stable, higher field magnets, key engineering hurdle in achieving commercially viable fusion energy. Even in fundamental science, the pursuit of near-absolute zero environments sharpens our view of the cosmos. The Laser Interferometer Gravitational Wave Observatory, or LIGO, which first detected the space-time ripples predicted by Einstein a century prior in 2015, represents an extraordinary triumph of low-temperature engineering. The core mirrors, suspended as the interferometer arms, must be shielded from all forms of thermal noise. Any random vibration caused by residual heat in the mirror material would introduce noise indistinguishable from a genuine gravitational wave signal from merging black holes light years away. Consequently, the massive fused silica mirrors are actively cooled to near absolute zero environments to minimize this thermal jitter, allowing the detection of distortions in spacetime smaller than 1/10,000th the diameter of a proton. The philosophical weight of the absolute zero concept forces us to confront the distinction between the physical impossibility of reaching it and the conceptual perfection it represents. Absolute zero is the thermodynamic zero, the null state against which all other energy states are measured. It is the boundary condition of energy. If we were to violate this boundary, as the initial premise suggests, by imposing this state upon ourselves, the result is not death in the conventional sense, which implies a process, but rather an instantaneous transition into a fundamentally different ontological state, that of fixed matter obeying only the minimal, unyielding constraints of quantum mechanics. The cessation of time, the perfect crystal structure, the absolute stillness, these are not merely extreme conditions, they are the physical expression of a universe stripped of its dynamic essence, a profound and permanent silence from which no signal, no chemical change, no awareness could ever re-emerge, eternally preserved in the perfect, cold snapshot of the moment of immersion. The very notion of what would happen next becomes meaningless, for next requires now to transition, and at absolute zero, the possibility of transition is utterly extinguished by the universal law that guards the ultimate energetic flaw. The reality, however, remains that this perfect stillness is forever barred by the inherent quantum restlessness of existence, ensuring that the universe, even at its coldest, remains infinitesimally, yet fundamentally, alive.